California has a burning volcano that is not really a volcano at all. It sits near the Salton Sea, bubbling through mud, salt, steam, and gas, as if the desert floor is quietly breathing. But beneath that strange surface is something much larger: hot brine, unstable ground, hidden faults, and one of the most active tectonic zones in North America. Scientists are watching it because this small, restless patch of mud may be a surface sign of deep pressure, heat, and movement below. Stay with this video until the end, and if calm science stories like this help bring the universe and Earth into focus, please like, subscribe, and support the channel. Southern California holds a wide, dry basin where the land seems open and still. The horizon lies low beneath a pale sky, and the light spreads across broad flats of dust, salt, scrub, and distant ridges. Heat gathers quietly over the ground. It rises from roads, bare soil, and dry washes in soft, wavering lines. The air carries little moisture, and the shapes of the land appear sharp in the morning, then softened by brightness as the day grows warmer. This outer region is not a single empty desert, but a basin shaped by water, heat, wind, and long movement in the earth. It rests within a larger landscape where mountains frame low ground, where old shorelines remain faintly visible, and where the surface gives only a calm first view of a more active setting. The basin sits in a place where dryness is not accidental. Air moving across the region loses much of its moisture before it reaches the low interior. Mountains stand as barriers, and the land behind them receives less rain than coastal areas. Storms arrive at times, but long dry periods dominate. Under this pattern, plants grow with caution: creosote bush, saltbush, grasses, and scattered desert shrubs occupy the ground where soil and water allow them. Their spacing gives the land an open texture. Between them, bare earth remains exposed to sun, wind, and sudden runoff. The surface looks simple, yet it records many small exchanges between climate and ground. Each dry season leaves dust. Each rare, strong rain cuts channels and moves sediment. Each windy day lifts fine particles and sets them down again. The broad basin floor appears level from a distance, but it contains shallow rises, old watermarks, soft depressions, and crusted patches. Some areas hold light-coloured salt left behind by evaporating water. Other areas show darker soil mixed with organic material, clay, or minerals. The colours remain muted, often tan, grey, brown, and white, with occasional red or yellow tones where iron and other compounds affect the ground. In the far distance, ridges and mountains form a quiet rim. They are not decorative boundaries. They are the raised edges of a region shaped by the stretching and shifting of the crust. Their slopes shed sediment into the low basin, grain by grain and flood by flood, building fans of sand and gravel that spread outward from the highlands. The surface region also carries the memory of lakes that have come and gone. In this part of California, water has at times filled low areas when river flow, climate, and drainage patterns allowed it. At other times, evaporation has removed water faster than it arrived, leaving salt and fine sediment behind. This pattern creates a landscape where dryness and former water exist together. A white crust may mark old evaporation. Smooth clay may point to quiet water that once settled fine particles. Slight terraces may show where shorelines paused. These features do not speak loudly, but they give the basin a layered appearance. The land is dry, yet it is not untouched by water. It is open, yet it is not empty. Heat is one of the first forces felt in this outer zone, Surface heat comes from the sun, which warms bare ground efficiently when cloud cover is limited. During the day, rock, road, sand, and salt absorb energy. Near the ground, the air becomes warmer than the air above it. This creates shimmering views and a sense of slow motion even when the land itself is still. At night, the same open sky allows heat to escape quickly, and temperatures may fall. This daily rhythm shapes plants, animals, soil crusts, and human activity. It also gives the basin its visible character, because light and heat alter the way distance is seen. A feature that seems close may remain far away. A flat surface may appear to tremble without moving. Dust is another part of the outer landscape. Fine particles form when rock breaks down, when dry lake beds are exposed, when fields or roads are disturbed, and when wind crosses loose sediment. Dust travels easily through dry air. It can veil the mountains, soften the horizon, and settle as a thin film on plants and structures. In a basin, dust is not only a surface nuisance, it is part of the sediment cycle. Material erodes from high places, moves through washes, spreads across flats, dries, and may rise again with wind. Over long periods, such movement helps build and reshape the shallow surface. It also shows how connected the outer basin is to the ridges around it. The outer setting includes human marks as well, though they sit within a much older natural framework. Roads cross the flat land. Fields, canals, power lines, and settlements occupy parts of the basin where water management and engineering make work possible. Human systems bring order to some surfaces and disturbance to others. Irrigation can add water to places that would otherwise remain dry. Drainage can carry salts and sediment. Roads can cut across old natural paths. Yet even where human activity is clear, the larger controls remain present. Heat still rises, dust still moves, the ground still settles, cracks, and crusts. The basin remains a place where natural processes and human use overlap without becoming the same thing. From this outer view, the word volcano can mislead. A familiar volcano may be imagined as a steep cone, a summit crater, and glowing lava. This California basin does not begin with that shape. Its first appearance is low, broad, and quiet. The land offers no towering cone at the horizon. It presents dry flats, low ridges, salt surfaces, and a sky that seems larger than the ground. The volcanic connection here belongs to setting and process rather than to a dramatic mountain form. The basin lies within a region of active geology, where heat and crustal movement are important. At the surface, however, those deeper forces are mostly hidden by sediment, dryness, and distance. The calm of the outer basin is therefore a real calm, but it is not complete stillness. The land changes slowly through evaporation, erosion, sediment movement, heating, cooling, and the repeated action of rare water. It is a quiet exterior over a complicated Earth system. Observations show a region shaped by desert climate, former lakes, salt accumulation, fault-bounded lowlands, and geothermal influence. It remains uncertain in any single view how much change is happening beneath a given patch of ground, because the surface often conceals the pathways below. The outer landscape gives only the broad frame. It shows the basin as a dry, bright, low place, where the first signs are subtle, and where the deeper story begins beneath an ordinary-looking desert floor. Closer to the Salton Sea margin, the broad desert basin becomes a place where land and water meet unevenly. The shore is not a clean line. It shifts across shallow flats, soft mud, crusted salt, low berms, and exposed sediment. In some places, the water lies calm and dull beneath the sun. In other places, the ground beside it is dry, cracked, and pale. The surface carries the marks of recent wetness and recent retreat at the same time. A thin band of damp soil may sit beside a band of powdery salt. A smooth patch of clay may lie near broken shell fragments, dead plant matter, and wind-blown dust. This margin is a changing outer ring around a lake that has been strongly shaped by climate, river inflow, evaporation, and human water use. The Salton Sea is a large inland lake in a low basin with no natural outlet to the ocean. Water enters mainly through agricultural drainage, smaller streams, and occasional storm runoff, while water leaves mostly by evaporation. This simple balance gives the shoreline its restless character. When inflow is higher, the lake surface can rise and cover low ground. When inflow is lower or evaporation dominates, the water retreats and leaves wet sediment open to sun and wind. Because dissolved salts remain when water evaporates, the remaining lake water becomes salty, and the exposed ground can develop pale mineral crusts. The shore zone therefore records both water and loss of water. It is a boundary that is always being rewritten. The air near the margin often carries a mineral smell, especially where organic material, stagnant water, and exposed sediment interact. The scent can come from decaying algae, wet mud, sulfur compounds, and salty water. These odours are not separate from the science of the place. They are signs of chemical and biological processes in shallow water and wet sediment. Warm temperatures allow microbes to act on organic matter. Low oxygen conditions can develop in mud and bottom water. In such settings, some microbes use sulfur compounds in ways that can produce hydrogen sulfide, a gas with a strong odour at low concentrations. The presence of an odour does not by itself describe danger, but it shows that the margin is chemically active. The shoreline surface may look firm, but it can change over short distances. A dry crust can cover soft mud. A pale salt layer can hide damp clay below. Fine sediment can hold water in a way that makes the ground weak even when the surface appears solid. This happens because clay and silt particles are small, flat, and closely packed. Water clings between them, and the ground can lose strength when disturbed. Along a retreating lake margin, new surfaces are exposed before they are fully dried. Compacted, or stabilized by plants, the result is a shore zone that is uneven underfoot, with some areas hard and brittle, some sticky and soft, and some broken into curling plates by drying. Evaporation shapes this region with steady force. Under hot, dry air, water at the surface changes into vapour and leaves salts behind. The salts may form white or grey crusts across mud flats, along the edges of pools, and around small depressions. These crusts may contain different minerals depending on the chemistry of the water and sediment. Some dissolve again when wetted, others remain as rough patches. As the surface dries, the ground contracts and cracks. Polygonal patterns can form where shrinking mud pulls apart. The cracks may later catch dust, seeds, or new salt crystals. Such small patterns give the shore a detailed texture, but they also mark repeated cycles of wetting and drying. The margin also contains evidence of human alteration. The modern Salton Sea formed in the early 20th century when Colorado River water entered the low basin through failed irrigation controls and filled the depression for nearly 2 years. Since then, the lake has depended greatly on managed water moving through farms and drainage channels. Agricultural return flow carries dissolved salts, nutrients, and fine sediment. Nutrients can support algae growth, while salts increase because evaporation removes water, but not most dissolved minerals. Human water decisions across the region influence lake level, exposed shoreline, dust risk, habitat, and water quality. The shore is natural in its physical setting, but it is modern in its dependence on managed inflow. As water retreats from parts of the margin, exposed lake bed becomes a source of dust. Fine particles that settled in quiet water can dry into loose surfaces. When wind crosses them, the smallest grains may rise into the air. The risk depends on moisture, crust strength, wind speed, surface roughness, and whether plants or engineered covers hold the ground in place. Dust from exposed lake bed may contain salts and other materials from the lake and surrounding drainage. Scientists study this dust because it can affect air quality for nearby communities and ecosystems. The shore is therefore not only a line on a map, it is also an active surface that can move into the air as fine material. Water at the margin supports and stresses life at the same time. Birds use shallow areas, wetlands, and exposed flats for feeding and resting. Fish have lived in the lake under certain salinity and oxygen conditions, though high salinity, heat, nutrient changes, and low oxygen can create severe stress. Algae and microbes respond quickly to warm, nutrient-rich water. Plant life along the edge depends on salinity, moisture, and disturbance. Some plants tolerate salt and grow in patches, helping trap sediment and reduce wind erosion. Other areas remain bare because the ground is too salty, too unstable, or too recently exposed. Life here is present, but it is shaped by limits. This shore zone also shows how shallow water can hide deeper processes without revealing them directly. Bubbles may rise in some wet areas because gases form or escape through sediment. Soft spots may slump where the ground is saturated. Small pools may appear where water collects in low places. These features are part of the margin's surface behavior, and they can result from several causes, including decay of organic material, trapped air, groundwater seepage, and gas moving through mud. Careful observation is needed before any single cause is assigned. The margin teaches that similar surface signs can have different sources, and that a calm pool or crusted flat may be more complex than it first appears. At this region of the setting, the story remains at the edge of the lake. It is a zone of contact between desert air and inland water, between managed inflow and evaporation, between soft sediment and salt crust. The surface changes because water advances and retreats, because salts accumulate, because mud dries and breaks, because wind lifts fine particles, and because human systems alter the balance. The Salton Sea margin is therefore unstable in a slow and physical way. It does not need sudden motion to change. It changes through exposure, drying, settling, chemical concentration, and the steady pressure of a hot basin climate. Within this shore zone, the land begins to show that the quiet desert exterior is not uniform, and that the ground near the water holds its own restless science. Beyond the shifting shore and its exposed flats, the setting narrows into the geothermal field, where the ground belongs to a wider system of heat moving upward through the crust. A geothermal field is an area where underground heat, water, and permeable rock work together closely enough that warmth reaches shallow levels in measurable ways. At the surface, the region may still look like desert, farmland, roads, canals, and low industrial structures. The air may still seem ruled by sun and dust. Yet beneath this ordinary exterior, temperatures rise more quickly with depth than they do in many other places. The heat does not spread evenly. It follows weaknesses, layers, fractures, and zones where water can move. In most parts of the Earth, temperature increases gradually downward. This increase is called the geothermal gradient, meaning the rate at which the ground becomes warmer with depth. In the Salton Trough region, the gradient is unusually high because the crust is thin, stretched, faulted, and influenced by deep heat. Sediment fills the basin in thick layers, but the heat below it is not distant in geological terms. Drilling and scientific measurements show that hot fluids exist at depths reachable by wells. These fluids are not simple clean water, they can be dense brines, meaning very salty waters, carrying dissolved minerals from hot rock and sediment. Their presence makes the field both scientifically important and physically demanding. The geothermal field does not need a tall volcanic cone to exist. It depends on heat, fluid, and pathways. Heat rises from deeper rock. Water circulates through the subsurface. Cracks, faults, and porous layers allow movement. When water descends or sits in hot zones, it warms and dissolves minerals. If pressure and pathways allow it, the heated fluid may rise again. At the surface, only parts of this system become visible: steam, warm ground, mineral deposits, and bubbling mud can mark places where the system approaches daylight. In other places, the same system remains hidden beneath dry soil, roads, or fields. The visible signs are scattered because the underground pathways are scattered. The Salton Sea geothermal area is one of the most notable geothermal systems in the United States. It lies near the southern part of the lake, where heat flow is high and hot. Brines are present underground. Energy facilities use wells to bring hot fluid upward, draw heat from it, and return fluid underground. This process can generate electricity because heat from the earth can boil working fluids or produce steam that drives turbines. The industrial presence may appear separate from the natural landscape, but it exists because the natural heat system is unusually strong. Pipes, wells, separators, and power plants are surface expressions of a deeper thermal structure. The water in this geothermal field is important because heat alone does not explain the surface behavior. Dry hot rock can remain hidden, hot water can move, carry dissolved material, change pressure, and feed surface features. In the subsurface, water may travel through sand layers, fractured rock, and fault zones. It may also be trapped in pockets where pressure builds. When hot brine rises, pressure decreases, and some dissolved gases can separate from the liquid. Steam can also form under certain conditions. These changes affect how fluids move and how energy reaches shallow ground. The field is therefore not simply hot, it is a moving system of heat and fluid. The chemistry of geothermal fluid reflects contact with rock over time. Hot water is a powerful solvent compared with cold water. It can dissolve salts, metals, silica, and other compounds from the rocks and sediments it touches. In the Salton Sea system, the brines can be especially rich in dissolved material. This creates challenges for energy production because minerals can form scale inside pipes and wells when temperature or pressure changes. Scale is a hard mineral buildup, similar in idea to deposits in a kettle, but formed under far hotter and more complex conditions. Corrosion can also affect metal equipment. These industrial issues reveal a scientific fact about the field: the underground waters are chemically active. At the surface of the geothermal field, the signs of heat may be subtle or direct. Warm soil can dry differently from nearby ground. Mineral crusts can form where small amounts of fluid reach the air and evaporate. Steam may rise from vents when conditions are right. Mud and water may bubble where gas escapes through saturated sediment. Some places may show sulfur staining or pale deposits. Others may be quiet for long periods, then shift as pathways open or clog. A vent can weaken when minerals seal a passage. A nearby weak spot can become more active if pressure finds another route. The pattern is not random, but it is complicated because it depends on underground pathways that cannot all be seen from the surface. The geothermal field also connects to the physical softness of the basin. Thick sediment blankets the area. Sediment can compact, fracture, shift, and respond to water pressure differently from solid crystalline rock. Layers of clay may hold water back. Sandier layers may allow easier flow. Faults can cut across both, creating vertical pathways. Heat moving through such a layered body does not behave like heat moving through a single block of stone. It bends around barriers, follows fluids, and changes with depth. The field is a three-dimensional system, but the surface offers only a thin, partial map of it. Scientists study the field using wells, temperature measurements, chemical analysis, seismic monitoring, satellite observations, and mapping. Wells provide direct information at depth, but only along drilled paths. Chemical samples show what fluids have touched and what they carry. Seismic instruments record small earthquakes and vibrations that may reveal active faults or fluid movement. Satellite radar can detect slight changes in ground elevation over time. Though such measurements require careful interpretation, each method shows one part of the system. Together, they describe a place where high heat flow, salty fluids, faulted crust, and soft sediment interact. The geothermal field is not terrifying in a dramatic sense. It is concerning because it is powerful, hidden, and close to the surface in certain areas. The heat is real, the gases are real, the fluids are hot, salty, and pressurized at depth. The ground can be weak where water and gas disturb sediment. Human infrastructure may sit near active natural processes. Observations indicate that this region contains a strong geothermal resource tied to an active tectonic basin. It remains uncertain in detail how every shallow vent and mud feature connects to the deeper reservoir, because pathways can be narrow, shifting, and difficult to trace. In this region, the outer landscape of water and salt gives way to a deeper pattern of heat, and the quiet surface begins to show the presence of a warm system underneath. At the surface of the geothermal field, the so-called burning volcano appears as a low, unsettled place rather than a mountain. The ground may rise only slightly above the surrounding flats, with wet mud, crusted edges, shallow pools, and small openings where gas and water disturb the surface. Its shape can change because the material is soft. A rim may slump, a vent may widen, mud may spill across a nearby patch and dry into a rough skin from a distance. The feature can seem like a dark wound in pale ground. From closer range, it is a surface expression of heated water, gas, and fine sediment, not a cone built by lava. The word burning can come from appearance and activity, but the surface is not burning in the ordinary sense. There may be steam, warm vapor, dark wet mud, mineral staining, and gas bubbling through water. The ground may look scorched where mud is dark or where sulfur and other minerals change the color of crusts. Heat may be present, yet the process is not the same as open flame. Fire is rapid chemical reaction with oxygen that releases heat and light. The mud feature instead releases heat already held in the earth and carried by water and gas. Its motion comes from pressure and buoyancy, not from combustion. The word volcano can also mislead. A true volcano is a place where molten rock, ash, and volcanic gases reach the surface from deeper magmatic sources. Lava builds flows or cones. Ash can fall from eruption columns. Magma may break rock as it rises. A mud pot or mud volcano can look active and eruptive, but its material is different. Mud pots form where hot water, gas, clay, and fine sediment mix near the surface. Mud volcanoes, in a broad sense, are features where mud and gas are pushed upward through weak ground. Some are linked to petroleum systems, some to geothermal systems, and some to tectonic compression. In this California setting, the surface feature belongs to a geothermal and sedimentary environment, rather than to a lava-producing volcanic cone. The mud itself is central to the appearance. Fine particles of clay and silt mix with water until the ground behaves like a thick fluid. Clay is made of very small mineral grains that can hold water between their surfaces. When enough water is present, the mixture becomes plastic, meaning it can deform without breaking. When gas rises through it, bubbles push upward and burst at the surface. If the mud is thin, the bubbles may open easily and make small circular ripples. If the mud is thick, the bubbles may lift domes that collapse slowly. This gives the surface a breathing or pulsing motion, although the process is mechanical rather than alive. The sound of such a place, when present, comes from simple physical actions. Gas rises, bubbles stretch, mud films break, wet sediment slumps into openings, small splashes fall back into pools. The pace can be uneven because gas does not escape as a perfectly steady stream. It gathers in pockets, rises through weak zones, then releases. The surface may rest for a moment, then a bubble opens and dark mud rolls outward. This activity can seem dramatic because it is visible, but the forces involved are common in geothermal ground. Heat warms water, gas separates or forms, pressure seeks an opening, soft sediment yields. Steam may rise when warm or hot water meets cooler air, especially in the morning or in humid conditions. Steam is water vapor that condenses into tiny droplets when it cools. What is seen as a pale plume is often not pure invisible vapor, but condensed droplets suspended in air. The amount visible depends on temperature, wind, humidity, and the rate of water release. A feature may look more active on a cool morning than in the heat of the day, because the same vapor condenses more easily in cooler air. This difference shows why surface appearance must be interpreted carefully. The visible plume is partly a sign of heat and partly a result of weather. Mineral crusts around the mud pots form where water reaches the surface and evaporates. Dissolved material is left behind as pale, yellowish, reddish, or grey deposits. Some crusts are salty, some contain sulfur compounds, some include silica or iron-bearing minerals. These deposits can make the ground look burned or stained. The colours are not random decoration. They show that the water has travelled through sediment and rock, dissolved substances, and then lost water to the dry air over time. Repeated wetting and drying build thin layers around vents and pools. The crust can be brittle and hollow, especially where gas continues moving beneath them. The edges of a mud pot are often fragile because the surface is built from the same material being disturbed. A ring of dried mud may surround a wet centre. Beneath the ring, water can remain trapped. Gas can undercut the rim. Small collapses can occur when the support below weakens. The vent may migrate by inches or more as old passages clog and new ones open. Mineral deposits can seal one path, while pressure opens another nearby. In soft sediment, this movement does not require large force. It only requires a difference between pressure below and strength above. The result is a surface that changes shape slowly and sometimes abruptly in small ways. The feature's surface temperature may vary across short distances. One patch of mud may be warm. Another may be cooler because it receives less rising fluid or more shallow groundwater. A vent may be hotter than its rim. A pool may cool quickly at the surface while remaining warmer below. Such variation is typical in geothermal areas because fluid flow is channeled. Heat does not rise everywhere in a smooth blanket. It arrives through openings, layers, and wet pathways. This is why some places bubble while nearby ground remains dry. The field is not uniformly active at the surface. It is patterned by hidden passages. The apparent threat of the surface mud pot is not that it is about to erupt like a classic volcano. The concern lies in unstable ground, hot fluid, gases, and the difficulty of knowing where weak zones extend beneath crusted sediment. A firm-looking surface may be thin. A vent may release gas in sudden pulses. Mud can be hot enough to injure. Some gases may be harmful in high concentrations or in low areas where air movement is poor. Observations indicate that these surface features are signs of an active geothermal system interacting with soft sediment and shallow groundwater. It remains uncertain from surface appearance alone how deep each pathway reaches or how it changes through time. In this region, the burning volcano is not a mountain of fire, but a restless mud surface where the hidden heat of the basin touches open air. Within the restless surface, the next region is the vent itself, where gas rises through water, mud, and weak sediment. A gas vent is an opening or pathway that allows gas from below to escape into the air. It may look like a small hole, a bubbling pool, a wet crack, or a patch of mud that repeatedly swells and breaks. The opening may be only a few centimeters wide, or it may be part of a larger disturbed area. Its shape matters less than its function. It is a release point. Beneath it, gas gathers, moves upward, and passes through the shallow ground because pressure below is greater than pressure at the surface. The main gas in many mud volcano and geothermal vent settings near the Salton Sea is carbon dioxide. Carbon dioxide is a colourless gas that can come from several sources, including deep geological processes, reactions between hot fluids and carbonate minerals, and biological decay in sediment. In this region, the exact mixture can vary from one vent to another, because each pathway may connect with different layers and fluids. Carbon dioxide does not burn under normal conditions. It is heavier than ordinary air, so in still conditions it can collect in low places. In open desert air, wind usually disperses it, but near vents and depressions the gas remains an important part of the hazard. Water vapour is also present where heated water reaches shallow levels. Some of it remains invisible as vapour. Some condenses into pale steam when it meets cooler air. This vapour carries heat from the subsurface and may also carry traces of volatile compounds, meaning substances that can move easily as gas. The amount of visible steam does not always match the amount of gas release. A vent may release much carbon dioxide with little visible vapour, or it may appear steamy because warm moisture condenses in cool air. For this reason, the surface plume is only one sign. The invisible gases can be just as important as the visible ones. Hydrogen sulfide may occur in some geothermal and organic-rich wet settings. It has a strong odour at very low concentrations, often compared with rotten eggs, though the smell is only a warning at low levels and cannot safely measure danger. At higher concentrations, hydrogen sulfide can reduce the ability to smell it, which makes odour unreliable. It can form when sulfur compounds are changed by microbes in low oxygen mud, and it can also be associated with geothermal fluids. In the Salton Sea region, sulfur odours near mud pots and wet sediments fit known chemical and microbial conditions. The presence and concentration of hydrogen sulfide can vary with vent activity, water level, temperature, and air movement. Methane can also be part of shallow gas in sedimentary environments, especially where organic matter breaks down without oxygen. Methane is a colourless gas and can burn when mixed with air in the right proportions and exposed to ignition. In many mud pot settings, however, carbon dioxide may dominate over methane. The balance depends on the source layers, temperature, biological activity, and the path the gas follows. It is important to separate appearance from composition. A bubbling vent does not automatically mean flammable gas. Scientific sampling is needed to identify what is rising, and repeated sampling may be needed because gas chemistry can change over time. The movement of gas through mud follows simple physical rules, but the result appears irregular. Gas forms or accumulates below. It pushes into pore spaces, which are the tiny openings between grains of sediment. If the grains are wet, the gas must displace water or move through small connected gaps. Fine mud resists flow more than coarse sand, so gas may gather until pressure is high enough to open a temporary channel. Once the channel opens, gas escapes quickly. Pressure drops, and the channel may collapse or seal again. This cycle creates pulsing bubbles. The vent does not breathe, but the release can look rhythmic because pressure builds and falls. Gas also changes the strength of the ground. Sediment is strongest when grains press firmly against one another. Water pressure can reduce that grain-to-grain contact. Gas bubbles can disrupt it further. When gas and water move upward through fine sediment, they loosen the structure, lift particles, and make the mixture less stable. A surface that appears solid may contain voids or saturated zones below. If gas removes support or mud flows outward, small collapses can form. In this way, gas is not only something escaping from the ground, it is also an agent that rearranges the shallow sediment as it passes. The vent pathways are often narrow and changeable. Minerals can precipitate, meaning they form solid deposits from dissolved substances, and these deposits can partly seal an opening. Fine particles can settle into a channel and clog it. A sudden pulse of gas can clear a route. New cracks can open nearby if pressure finds weaker ground. The surface pattern of bubbling may therefore shift without a large change in the deeper system. A vent can quiet down while another becomes active a short distance away. The gas follows the easiest available path, and in soft, wet sediment, that path is not permanent. Air above the vent forms another small region of concern. Gas leaves the ground and mixes with the atmosphere. Wind, temperature, and the shape of the surface control how quickly it disperses. During breezy conditions, gas spreads and dilutes. During still conditions, heavier carbon dioxide can remain closer to the ground, especially in hollows. Warm air rising from the surface can lift vapour. Cooler air can keep gases near low areas. These effects are local and change through the day. They show why a vent is not only an underground feature. It includes the shallow air immediately above it, where invisible gases enter a living environment. Measurements help make this hidden region understandable. Scientists can collect gas samples, analyze carbon isotopes, measure temperature, and monitor flow rates. Isotopes are forms of an element with different atomic weights, and they can help identify whether carbon dioxide is more likely linked to deep geological sources, biological sources, or chemical reactions. Field instruments can detect gases that human senses cannot measure reliably. Such work shows that vents are not simple holes. They are chemical signals from below, filtered through water, sediment, and air. Each gas sample carries information about depth, temperature, reaction, and pathway, though the message is never complete. The gas vent region is therefore quiet in appearance only when viewed from far away. At the scale of mud, pores, bubbles, and shallow air, it is active and changing. Carbon dioxide can rise unseen. water vapour can appear and vanish with weather. Hydrogen sulfide may mark sulfur chemistry. Methane may occur in some settings where organic matter and low oxygen conditions allow it. Observations indicate that gas release is a central part of the mud pot system, helping drive bubbling. Weakening ground and carrying chemical evidence of subsurface processes, it remains uncertain without direct measurement how much of each gas is present at any moment in a single vent. The surface disturbance is only the visible edge of a small, hidden atmosphere rising through the ground. Below the gas vent, the next region is the boiling sediment, where mud, water, gas, and heat combine in a shallow body of disturbed ground. The word boiling can describe the appearance, but it does not always mean the mud is at the boiling point of pure water. In a geothermal mud pot, bubbles rise and burst because gas moves upward through wet sediment, and because hot water may add steam or vapour, the surface can look as if it is cooking, with dark circles opening, closing, and rolling over themselves. The process is physical and chemical rather than simple kitchen boiling. It depends on temperature, pressure, grain size, water content, and gas flow. Sediment in this region is made of fine particles that have settled, washed in, or been altered by hot fluid. Clay and silt dominate many soft mud zones. Clay particles are extremely small and carry surface charges that help them hold water. When water fills the spaces between them, the mud becomes smooth and cohesive. Cohesion means the material sticks together. It may bend, smear, and stretch before breaking. This property allows bubbles to rise as rounded pockets, lifting a skin of mud until it tears. If the sediment were coarse sand, gas would pass through more easily and the surface would look different. Fine mud makes the motion slow, thick, and rounded. Heat changes the behaviour of this wet sediment. Warm water lowers the thickness, or viscosity, of some mud mixtures, making them flow more easily. It can also speed chemical reactions that alter minerals. In hot acidic conditions, some rocks and minerals break down into clays, which can thicken the mud and make it more able to trap gas. Temperature also affects gases dissolved in water. As water warms or pressure decreases, gas can come out of solution and form bubbles in the shallow sediment. These effects work together. Heat helps create and move the fluids that disturb the mud, while the mud itself controls how that disturbance appears. Pressure is strongest below the surface and weaker at the open air. Gas and water move upward because of this pressure difference. In a soft mud layer, the upward force must overcome the weight and strength of the material above it. When pressure is low, gas may seep slowly through tiny spaces. When pressure builds, it may open a larger passage. The passage can be temporary. Mud flows around it, collapses into it, or seals it with fine grains. Then pressure begins to build again. This repeating cycle produces uneven pulses. The ground does not need a single permanent pipe. It can create and lose small pathways many times. The mud pot's apparent churning comes from these repeated releases. A bubble begins as a pocket of gas below the surface. It grows or rises through the wet sediment. As it approaches the top, the weight above it becomes less. The bubble expands. The mud skin stretches over it. When the skin becomes too thin or weak, it breaks. Gas escapes into the air, and the surrounding mud falls inward or splashes outward. A small crater may remain for a moment, then fill again as mud flows back. The action is gentle at times and sharper at others, depending on gas volume, mud thickness, and the height of the burst. Water content decides whether the surface behaves like soup, paste, or cracked clay. With more water, bubbles pass through a liquid pool and make ripples. With less water, the mud becomes thicker, and bubbles push up slow domes that burst with a heavy fold. With still less water, the surface stiffens and cracks, allowing gas to escape through narrow openings. Around one mud feature, all these textures may exist together. A wet center may bubble steadily, a rim may dry into plates. A nearby patch may hold hidden moisture under a crust. This unevenness is part of the hazard, because appearance does not always show the strength of the material below. The sediment can also be undermined from within. Gas rising through wet mud can carry small particles upward, leaving tiny voids. Water moving laterally can wash out fine material. Repeated bubbling can loosen the grain structure. When support is reduced, the surface may sag or collapse. The collapse may be small, only a soft rim sliding into a pool, or it may enlarge a vent. In a place where the ground is already saturated and warm, these changes can occur without much warning. The material is not solid rock. It is a soft mixture that remembers every pulse of gas and every shift in water. Chemistry contributes to the texture of the mud. Hot fluids may contain dissolved salts, acids, silica, iron, sulfur, and other compounds. Acidic water can form when gases such as carbon dioxide and hydrogen sulfide dissolve in water and react with oxygen or minerals. Acidity is a measure of how strongly water can donate hydrogen ions, and in plain terms it affects how water dissolves and changes minerals. Over time, acidic hot water can break down feldspar and other minerals into clay. This creates more fine material, which makes the mud smoother and better at trapping gas. The chemistry, therefore, helps build the physical character of the boiling sediment. Evaporation acts from above while heat and gas act from below. The top of the mud loses water to the dry air, a skin forms. Beneath that skin, mud may remain wetter and warmer. Gas then pushes against a layered surface, with soft material below and firmer material above. This can create bulges, cracks, and sudden openings. Salt and mineral deposits may strengthen some patches while leaving hollow spaces beneath. The same surface may be brittle at the top and weak underneath. The result is a ground that cannot be understood by colour alone, or by whether it looks dry. The shallow mud also records changes in weather and lake margin conditions. After rain, added water can thin the mud, dissolve salts, and alter bubbling patterns. During hot dry periods, the surface thickens and crusts. Wind can cool the surface, remove moisture, and spread fine dried sediment. Nearby groundwater changes may raise or lower the amount of saturation in the mud. These surface and shallow subsurface effects do not replace the deeper heat system, but they shape how it appears. The same vent can look different through seasons, days, or even hours because the upper sediment responds quickly. In this region, the movement remains confined to mud, water, and gas. It is not lava rising, and it is not a classic explosive eruption. It is the restless behavior of fine sediment under heat and pressure. Observations indicate that bubbling mud pots form where geothermal gases and fluids disturb shallow, water-rich deposits. The main concerns are unstable ground, hot mud, sudden collapse of crusts, and the possible release of gases near the surface. It remains uncertain from appearance alone how hot the deeper mud is, how thick the weakened zone may be, or which passage gas will choose next. The boiling sediment is a soft inner layer of the surface system, where the desert floor loses its firmness and becomes a moving mixture shaped from below. Around the boiling sediment, the next region is the zone of salt and minerals, where dissolved material leaves visible traces on mud, crust, and shallow water. This region forms at the contact between rising fluids, lake margin sediment, dry air, and strong evaporation. It may appear as pale crust, yellow staining, reddish patches, grey films, dark wet mud, or brittle rims around pools and vents. The colours and textures are not separate decorations on the surface. They are the remains of chemical movement. Water carries dissolved substances upward or sideways. Heat changes reactions. Air dries the surface. Minerals settle out and stay behind. Salt is common in this setting because the basin holds water without an easy natural outlet. When water evaporates, it leaves most dissolved ions behind. An ion is a charged particle formed when an atom or group of atoms gains or loses electrons. Sodium, chloride, calcium, magnesium, sulfate, and other ions can be present in the water and sediment. As water becomes more concentrated, some of these ions join into solid minerals. Ordinary table salt is sodium chloride, but natural salt crusts are often mixtures. Their exact composition depends on the source water, temperature, acidity, evaporation rate, and the minerals already present in the ground. At the mud pot surface, salts may form thin white skins that break under slight pressure. They may grow as powdery patches along drying cracks, or as rough rings where a pool once stood. These deposits show where water has moved and vanished. A damp edge can dry and leave a bright line. A splash of mud can harden and become coated with crystals. A shallow film can shrink into irregular plates. The surface looks still after drying, but it is a record of motion. Each crust marks a small path taken by water before the air removed it. Sulfur compounds add another layer of chemistry. Sulfur can move through geothermal systems in several forms. Hydrogen sulfide gas may rise from below or form in low oxygen mud. When it reaches oxygen-rich conditions near the surface, it can take part in reactions that produce elemental sulfur or sulfate minerals. Elemental sulfur may appear yellow. Sulfate minerals can form pale or white deposits. Some sulfur reactions are helped by microbes, which gain energy by changing sulfur compounds from one form to another. These microbes are small, but their work can influence colour, acidity, and mineral formation in wet ground. The smell often associated with sulfur is not a mineral itself, but a sign of gas and reaction. Hydrogen sulfide can be detected by smell at low levels, though smell is not a reliable measure of concentration. In the mineral zone, odour may come and go with venting, wind, moisture, and microbial activity. A stronger smell may occur where wet sediment lacks oxygen and sulfur compounds are being transformed. A weaker smell may occur when wind disperses gas or when pathways are sealed. The ground's scent is therefore changeable, like the crusts and stains around it. Iron gives some surfaces red, orange, or brown tones. Iron-bearing minerals can dissolve in certain conditions and then precipitate when water chemistry changes. If iron-rich water reaches oxygen, iron can oxidize, meaning it reacts with oxygen and changes into forms that often have rusty colours. These colours may spread as thin films, stains, or small patches near flowing or seeping water. Iron colours can resemble burned ground, but they usually show chemical weathering rather than fire. The colour is the result of electrons shifting between atoms, not flames consuming material. Silica may also be present in geothermal fluids. Silica is a compound of silicon and oxygen, common in rocks and minerals. Hot water can dissolve silica from rock more effectively than cooler water. When the water cools, evaporates, or changes chemistry. Silica may form deposits. In some geothermal regions, silica builds hard sinter terraces or crusts. In the Salton Sea setting, the details depend on the fluid pathway and chemistry, but silica remains part of the broader mineral story. It shows how hot water can carry pieces of rock chemistry upward in dissolved form, then leave them near the surface as solids. Acidity influences which minerals dissolve and which remain. Acidic water can attack certain rock-forming minerals and help produce clay. It can dissolve metals and change sulfur compounds. Neutral or alkaline water may favour different deposits. The mud pot environment can contain small chemical gradients, meaning conditions change over short distances. A pool surface exposed to air may differ from mud a few centimetres below. A vent may carry gas that changes water chemistry at one point, while nearby crust dries under simple evaporation. These small differences create varied colours and textures within a compact area. Mineral crust can affect the physical behaviour of the mud pot. A crust may seal a vent temporarily and force gas to find another path. A hard rim may hold a pool in place until it breaks. Salt crystals can draw moisture from the air under some conditions or dissolve quickly when wetted. Sulfur and iron deposits can mark active seepage zones. Clay formed by chemical alteration can make mud smoother and more able to trap gas. The chemical zone is therefore also a mechanical zone. Minerals do not simply lie on the ground. They help shape how the ground opens, clogs, weakens, and hardens. Evaporation is especially important because it concentrates everything left behind. In a dry climate, surface water is temporary unless constantly renewed. A thin film can disappear quickly, increasing the concentration of dissolved salts until crystals form. Repeated wetting and drying can build layered crusts. The top layer may be fresh and powdery, while older layers below are compacted or mixed with clay. Wind can break and move some crystals. Rain can dissolve them and carry them into cracks. The mineral surface is always being built, removed, and rebuilt through small cycles. The mineral zone also connects the mud pot to the larger salton sea environment. The lake, exposed shore, agricultural drainage, geothermal fluids, and sediment all contain dissolved substances. Some salts reflect basin evaporation. Some compounds reflect biological activity. Some minerals reflect hot water moving through rock. The surface mixture may combine these sources. This makes the chemistry rich, but difficult to read from appearance alone. A white crust may not have a single origin. A yellow stain may show sulfur, but its path to the surface can involve gas, water, microbes, and air. Scientific analysis separates these possibilities by sampling water, gas, and solids. Laboratory tests can identify ions, minerals, isotopes, acidity, and trace elements. These measurements show how a deposit formed more clearly than colour alone. They can reveal whether a crust is mostly sodium chloride, gypsum, sulfur, silica, or a more complex mixture. They can also show how fluids have changed while rising and cooling. Yet even detailed samples represent moments and places. A nearby vent may differ. The same vent may change after rain, drying, or a shift in gas flow. In this region, the hidden system becomes visible as chemistry written on the surface. Salt crusts mark evaporation. Sulfur colours and odours mark gas and microbial reactions. Iron stains mark oxidation. Silica and clay point to hot water altering minerals. Observations indicate that the surface around the mud pots is shaped by repeated cycles of fluid movement, evaporation, precipitation, and chemical change. It remains uncertain without direct sampling which minerals dominate every patch, because similar colours can form by different paths. The salton mineral zone is a fragile skin over restless mud, where the dry basin air turns dissolved traces from below into visible signs. Beneath the salton mineral skin, the next region is subsurface water, the hidden moving part of the system that links heat, sediment, gas, and surface change. This water does not form a single clear underground river. It occupies pores between grains, small fractures, buried sand layers, clay boundaries, and openings along faults. Some of it may be shallow groundwater near the lake margin. Some may be deeper brine heated by contact with hot rock and sediment. Some may be trapped for long periods before moving again. Together, these waters form a complicated underground network in which pressure, temperature, chemistry, and permeability decide where flow can occur. Permeability is the ability of a material to let fluid pass through it. Coarse sand and gravel can be more permeable because their grains leave larger connected spaces. Clay is usually less permeable because its tiny particles pack closely and hold water tightly. The basin contains many sediment layers, so water does not move everywhere in the same way. It may pass sideways through a sandy layer, slow down where it meets clay, then rise through a fracture or disturbed zone. This layered movement helps explain why activity at the surface is patchy. A hot seep or bubbling vent may appear where a pathway reaches upward, while nearby ground remains quiet because water cannot pass as easily. The source of the water can vary. Rainfall is limited, but water can still enter the ground through rare storms. Washes, irrigation, canals, wetlands, and lake margin seepage. Agricultural water is especially important in the modern basin because it moves across fields and drains toward lower areas. Some shallow groundwater may carry salts, nutrients, and dissolved material from soils and drainage systems. Deeper geothermal brine has a different history. It has spent time in hot sediment and rock, dissolving minerals and gaining heat under pressure. These waters may mix in some places, but they are not all the same water. Their chemistry can reveal where they have been. Pressure controls much of the hidden motion. Underground water is held beneath the weight of sediment and fluid above it. In some layers, pressure may be higher than expected because water is confined by less permeable material. When a path opens upward, pressurized water and gas can move toward lower pressure at the surface. This movement does not need to be fast to be important. A slow seep can keep mud wet. A stronger rise can feed a bubbling pool. A pressure change can shift vent activity. The surface features are therefore not only signs of heat, they are also signs of water, finding release through a layered basin. Temperature changes the water's behavior. Warm water can hold and transport dissolved substances differently from cool water. At depth, under pressure, very hot water can remain liquid even above the boiling point it would have at the surface. As it rises and pressure falls, some of the water may flash into steam, meaning it changes quickly into vapor because the pressure is no longer high enough to keep it liquid at the temperature. This can add energy to the upward flow and help disturb mud. If the water cools before reaching the surface, it may deposit minerals and clog passages. The path of water is therefore shaped by both heating and cooling. The chemistry of subsurface water is one of its most important features. As water moves through hot rock and sediment, it dissolves salts, silica, metals, carbon dioxide, sulfur compounds, and other materials. The longer it remains in contact with hot minerals, and the hotter it becomes, the more chemically active it can be. In the Salton Sea geothermal system, deep brines are known for high salinity and complex dissolved content. This makes them valuable for scientific study in geothermal energy, but also difficult to handle. In the shallow natural setting, similar chemical principles operate on smaller visible scales, leaving crusts, stains, and altered clay. Subsurface water also affects gas movement. Gases can dissolve in water under pressure. Carbon dioxide dissolves and can make water more acidic. Hydrogen sulfide can dissolve and later escape where pressure drops or conditions change. Methane may form in low-oxygen organic-rich layers and move with groundwater or through separate gas pathways. When water rises, warms, cools, mixes, or loses pressure, gases may come out of solution and form bubbles. These bubbles can then loosen sediment and feed vents. The gas and water are not separate systems. They travel together, separate, and rejoin in changing ways. Mixing is especially important near the shallow surface. Deep hot water may encounter cooler shallow groundwater. Salty water may meet fresher water from irrigation or rare rain. Oxygen-rich water from near the surface may meet low-oxygen water from deeper mud. Each meeting can change chemistry. Minerals may precipitate. Gases may escape. Microbes may find new sources of energy. Clay may swell or weaken. A small mixing zone can therefore become a place of strong change, even if the flow is modest. The visible mud pot may sit above such a zone where waters of different histories come together. The water table, meaning the level below which pores are generally saturated, can rise or fall with lake level, irrigation, drainage, and seasonal conditions. Near the Salton Sea, shallow groundwater may be close to the surface in low areas. When the water table is high, mud can remain wet and soft. When it drops, upper layers dry, crack, and crust. Yet deeper pathways may still carry warm water upward. This creates a layered state in which the top appears dry while hidden wet sediment persists below. The result can be fragile ground, especially where gas continues moving through the saturated zone. Subsurface water can also transport heat sideways. Heat does not move only by conduction, which is the slow transfer of warmth through solid material. It also moves by convection, which is heat carried by moving fluid. In a geothermal field, convection can be very effective because hot water rises and cooler water may sink or enter from the sides. This movement redistributes heat through the shallow crust. It can create warm zones away from the deepest heat source and concentrate heat where pathways allow rising flow. The surface pattern of warmth therefore reflects water circulation as much as deep temperature. In soft sediment, flowing water can change the ground structure. It can dissolve minerals that once cemented grains together. It can deposit new minerals that harden other places. It can increase pore pressure, reducing the strength of sediment. Pore pressure is the pressure of fluid held in the spaces between grains. When pore pressure rises, grains press less firmly against one another, and the material can become weaker. This is one reason wet. Pressurized sediment may slump or liquefy more easily than dry compact ground. The same water that carries heat can also make the ground less stable. The subsurface water region is difficult to see directly, so it is studied through wells, temperature probes, water chemistry, geophysical surveys, and surface monitoring. A well can show temperature and chemistry at one point. Electrical methods can detect zones of salty water because brines conduct electricity well. Ground deformation measurements can suggest changes in pressure or fluid movement. None of these methods alone gives a complete picture. The underground water system is too layered and changeable for a single measurement to explain it fully. Still, the evidence shows a basin in which water is not passive. It is one of the main carriers of heat, gas, minerals, and pressure. In this inner region, the surface mud pot becomes easier to understand as the upper end of a water system. The bubbling, crusting, odour, heat, and weakness above all depend on water moving through sediment and rock below. Observations indicate that subsurface water in the Salton Sea geothermal area circulates through hot, faulted, mineral-rich ground and helps carry heat and dissolved material towards shallow levels. It remains uncertain how every small surface feature connects to every underground pathway, because flow can shift through narrow layers and fractures. The hidden water is the quiet transport layer of the system, moving through darkness, carrying the deep basin upward one dissolved trace at a time. Beneath the moving water, the next region is the fractured crust, where the basin floor is cut by faults, cracks, and weak zones that guide heat and fluid toward the surface. A fault is a break in the earth along which rock on one side has moved relative to rock on the other. In the Imperial Valley and Salton Trough, faults are not rare lines on a distant map. They are part of the structure of the region. Some are large and known from earthquakes and mapping. Others are smaller, buried beneath sediment, or difficult to trace at the surface. Together they make the crust more open, more uneven, and more able to transmit water, gas, and heat. The surface above the fractured crust may look flat, but the rock and sediment below are divided by movement. Long-term plate motion stretches and shears the region, meaning it pulls parts of the crust apart while also sliding them sideways. This creates breaks at different angles. Some faults allow horizontal movement, some allow vertical movement, some form step-like patterns that lower parts of the basin while raising or holding the edges. As the low basin fills with sediment, the faults continue to influence where layers bend, where pressure changes, and where fluids find openings. Fractures matter because intact rock can be a poor pathway for fluid, while broken rock can be much more permeable. A crack does not need to be wide to matter. Even a narrow opening can allow water or gas to pass if it connects deeper pressure to shallower levels. In sediment, faults can either help or block flow. A fault may grind rock and clay into a fine material that seals a pathway. Another part of the same fault may remain open enough to transmit fluid. This mixed behavior makes the underground system complicated. A fault is not simply a pipe. It is a zone of damaged material with changing properties. The fractured crust also controls where heat rises most effectively. Heat can move slowly through solid rock by conduction, but fluid moving along faults can carry heat upward faster. Where hot water rises along a fracture zone, the shallow ground may become warmer, and surface features may appear. Where a fracture is sealed, heat may remain deeper. The geothermal field is therefore patterned by the architecture of breaks beneath it. The surface mud pots, warm ground, and mineral deposits may sit above places where the crust has made a usable path, but the path can be indirect. Fluid may travel sideways through one layer, upward along a fault, then sideways again before reaching the shallow mud. In the Imperial Valley, sediment covers much of the fault structure. Thick deposits from the Colorado River and older basin environments fill the trough. These sediments can hide faults from direct view. A fault may reach close to the surface but leave only a subtle trace, or no visible trace at all. Scientists identify buried faults through earthquake patterns, drilling, geophysical surveys, and changes in sediment layers, seismic reflection methods, which use sound waves to image underground structures, can show tilted layers and breaks. Earthquake locations can reveal active planes of movement. Each method adds a partial view of the fractured region below the flat land. The San Andreas fault system lies within the broader tectonic framework of this area, and the southern end of that system approaches the Salton Sea region. Nearby fault zones, including those linked to the Imperial and Brawley seismic areas, help define the active crust. The details of fault connections beneath the southern Salton Sea are complex because the region is not a single clean break. It is a transition zone where sliding, spreading, and basin formation interact. This complexity is important. It means strain, which is stored deformation in rock, may be distributed across multiple structures rather than held on one visible line. Faults also create spaces where sediment can accumulate. As parts of the crust move downward relative to others, a basin forms. Rivers, floods, lakes, and wind then fill the low area with layers of sand, silt, clay, and salt-rich deposits. The more the basin sinks, the more sediment it can hold. This process buries older surfaces and creates a thick blanket above the deeper rock. The same faults that create the basin can later cut through its fill. Some fault zones may pass through soft sediment, where movement is expressed not as sharp rock faces but as warped, broken, or fluid-rich layers. Water pressure within faults can affect how easily they move. When fluid fills cracks under pressure, it can reduce the effective force pressing the sides of a fault together. Effective force means the part of the rock's weight and stress that actually holds grains or fault surfaces in contact. Higher fluid pressure can make sliding easier under some conditions. This does not mean every fluid change causes an earthquake. It means faults, fluids, and stress are linked. In geothermal regions, scientists pay attention to fluid pressure because natural circulation and human activity can both influence the shallow crust. Small earthquakes are common in active fault regions. Many are too small to be felt, but instruments record them. Their locations help outline where the crust is breaking or adjusting. In a geothermal area, some small earthquakes may relate to tectonic strain, some to fluid movement, and some to changes connected with geothermal operations. Separating these causes requires careful study. The fractured crust does not have one single behavior. It responds to regional plate motion, local pressure, temperature changes, and the movement of water through broken zones. Heat can also weaken the crust. Hot rock may deform differently from cool rock. Minerals may react with fluids, altering strength. Sediment at depth may compact and lose water. Fault zones may contain clay-rich material that slides more easily than strong rock. These properties influence how strain is stored and released. The region is not rigid in the simple sense. It contains strong blocks, weak layers, hot zones, pressurized fluids, and damaged fault material. This mixture allows both slow adjustment and sudden small breaks. The fractured crust beneath the mud features is therefore a hidden support system and a hidden weakness. It supports the upward movement of heat, gas, and fluid by providing pathways. It weakens the ground by dividing the crust and sediment into zones with different pressures and strengths. At the surface, only a small bubbling patch may be visible. Beneath it, the conditions depend on the arrangement of layers and breaks that formed over long geological time. The mud pot is not isolated from the crust. It is one expression of a region where the crust has been opened and altered by motion. In this region, the focus remains on the broken ground below the water-bearing layers. Observations indicate that the southern Salton Sea and Imperial Valley lie within an active faulted basin where fractures help guide geothermal fluids and gases. It remains uncertain in many specific places exactly which buried cracks connect a surface vent to deeper heat, because sediment cover hides much of the structure. The fractured crust is the inner framework behind the surface unrest. It is quiet most of the time, but it holds the pathways, stresses, and broken architecture that allow the desert floor to steam, bubble, and shift in selected places. Beneath the fractured crust, the next region is the plate boundary, where the larger motion of the earth gives the basin its deeper pattern. The Salton Trough lies in a zone where two great pieces of the outer earth move past and away from one another in a slow, steady way. These pieces are the Pacific Plate and the North American Plate. A tectonic plate is a broad slab of rigid outer earth made of crust and uppermost mantle, moving over deeper, weaker material. The movement is slow by human measure, only a few centimeters each year, but over geological time it is strong enough to pull land apart, shift mountains, open basins, and build pathways for heat. In this region, the plate boundary is not a single clean edge. It is a broad zone of faults, spreading centers, stepovers, and basins. A stepover is a place where motion transfers between fault segments that are offset from one another. When the arrangement pulls the crust apart, a low basin can form. The Salton Trough is part of a larger system that continues southward into the Gulf of California, where plate motion has opened a young ocean basin, northward. The motion connects with the San Andreas Fault System, where sliding dominates, the California Desert, the Salton Sea, and the Imperial Valley stand within this transition between sideways slip and crustal extension. The Pacific Plate moves generally northwest relative to the North American Plate. This movement is mostly horizontal along much of coastal and inland California. In the Salton region, however, the geometry changes. The boundary bends and steps in a way that creates pull-apart motion. Pull-apart means that parts of the crust are drawn away from each other as sliding continues. The ground between them can sink, stretch, and fracture. This helps explain why the basin is low and why thick sediment has collected there. It is not simply a hollow carved from above. It is a structural depression created by motion within the plate boundary. The rate of plate movement is small when observed from one year to the next, but the accumulated effect is large. A few centimeters each year becomes meters in a century, kilometers in a million years, and much more over longer spans. The crust cannot always slide smoothly. It may lock along faults, storing strain. It may creep slowly in some places. It may break suddenly in earthquakes. It may stretch and thin where the boundary opens. These different behaviors occur across the same general region because the plate boundary contains many structures with different orientations and strengths. The Salton Trough is closely related to the northern continuation of the Gulf of California rift system. A rift is a region where the crust is being pulled apart. In a mature ocean basin, rifting can eventually create new oceanic crust as magma rises and cools. In the Salton Trough, the process is partly hidden beneath thick sediment. The Colorado River has delivered enormous amounts of sand, silt, and clay into the region over time. These deposits bury the spreading environment and make the surface look like a low sedimentary basin, rather than an exposed oceanic rift. The plate boundary, however, remains active below the fill. This buried rift setting helps create the unusual heat of the region. Where crust is stretched and thinned, deeper hot material lies closer to the surface. Faults and fractures allow water to circulate. Magmatic heat may be present at depth, though the surface does not need to show a classic volcanic cone. The plate boundary supplies the large-scale reason that the geothermal field exists. Without the slow opening and sliding of the crust, the heat flow, faulting, and basin shape would be different. The mud pots are shallow features, but the larger cause begins with plate motion. The transition from the San Andreas Fault System to the spreading centers of the Gulf of California is one of the most important elements of this plate boundary region. The San Andreas system accommodates major sideways motion. Farther south, the Gulf of California contains spreading centers and transform faults, where new seafloor has formed in places. The Salton Trough sits between these modes. It holds evidence of extension, sedimentation, seismicity, and heat. The boundary is not fixed in one simple form. It changes style along its length, and the Salton region is one of the places where that change is expressed. At depth, the crust responds to plate motion by breaking, thinning, heating, and subsiding. Subsiding means sinking relative to surrounding areas. As subsidence creates space, sediment fills it. As sediment piles up, it adds weight and pressure. As faults move, they cut the layers. As heat rises, water circulates through them. Each part of the plate boundary process feeds the next. The basin is therefore not only a passive container, it is a growing structural feature tied to the continuing movement of the plates. The plate boundary also explains why earthquakes are part of the setting. When plates move, their edges do not glide evenly everywhere. Stress builds where faults resist motion. When the stress becomes greater than the strength of a fault patch, the rock slips and releases energy as seismic waves. Some earthquakes in the region are small and frequent. Larger earthquakes are possible on major faults. The presence of geothermal fluids and high heat can influence local behavior. But the broad source of tectonic stress is the relative motion of the plates. The mud features at the surface do not cause the plate boundary. They occur within it. This boundary is active in the present, but its processes are slow and uneven. A year may pass with little visible change on a particular patch of land. A small earthquake swarm may occur nearby. A vent may shift. A shoreline may retreat. A fault may remain locked. The plate boundary continues through all of these surface events because its motion is sustained by mantle convection and the global balance of plate forces. Mantle convection is the slow movement of hot, solid but deformable rock below the plates. It helps drive the plates, though the exact balance of forces includes slab pull, ridge push, and resistance along boundaries in different parts of the world. The terrifying aspect of this inner region is not a sudden image of fire. It is the scale difference between the small surface feature and the vast process beneath it. A bubbling mud pot is measured in meters. The plate boundary extends for hundreds and thousands of kilometers. The surface crust may appear dry and local, while its deeper setting belongs to the motion of continents and ocean basins. Observations indicate that the Salton Trough is part of an active transform and rift plate boundary, connecting the San Andreas system with the Gulf of California. It remains uncertain in detail how strain is divided at any moment among all buried faults and spreading structures. The plate boundary is the deeper engine of the region, moving slowly, shaping the basin, and giving the quiet ground its hidden tectonic life. Beneath the plate boundary structure, the next region is the magma heat source, where deep warmth enters the crust without forming a simple open volcano at the surface. Magma is molten or partly molten rock beneath the earth. It may contain crystals, liquid melt, and dissolved gases. In many volcanic landscapes, magma rises through the crust, erupts, and builds cones, lava flows, domes, or ash layers. In the Salton region, the heat is present in a different way. The surface does not need to show an active lava vent for magma-related warmth to affect water, sediment, and rock below. Heat can remain hidden, spreading through the crust and feeding the geothermal system from beneath. The plate boundary helps make this deeper heat possible, where the crust is stretched and thinned. Hot material from below can lie closer to shallow levels than it does beneath older, thicker crust. The connection with the Gulf of California rift system is important because rifting allows deep heat to rise and, in some places, allows magma to intrude into the crust. An intrusion is magma that enters rock underground and cools there instead of erupting. Such intrusions can release heat for a long time as they cool slowly. They can warm surrounding rock, drive circulation of underground water, and create a strong geothermal field without producing a tall volcanic mountain. In the Salton Sea geothermal area, scientific studies indicate very high temperatures at drillable depths, along with evidence that young igneous activity has affected the crust. Igneous means formed from molten rock. The region includes small volcanic features known as the Salton Buttes, which are low rhyolite domes near the southern shore of the Salton Sea. Rhyolite is a silica-rich volcanic rock, usually linked to thick, viscous magma. These domes show that magma has reached the shallow crust in the geologically recent past. They are not large volcanoes, and their quiet appearance can hide their importance. They mark a place where molten rock has interacted with the sediment-filled rift basin. The heat source below the geothermal field is not a single visible chamber that can be drawn with certainty from the surface. It is better understood as a region where hot intrusions, heated rock, and circulating brines are connected. Magma may enter the crust in sheets, dikes, or irregular bodies. A dike is a sheet-like intrusion that cuts across older layers. A sill is a sheet-like intrusion that follows layers more closely. As these bodies cool, they transfer heat to surrounding rock and water. The exact shapes, ages, and positions of all intrusions beneath the field are not fully known, because they are buried beneath sediment and can only be studied indirectly or through wells. Heat moves away from magma in several ways. It moves by conduction through rock, which is slow but steady. It also moves by convection when water circulates through hot zones and carries warmth upward. In a wet fractured basin, convection can move heat more efficiently than solid rock alone. Deep brines enter hot areas, gain energy, dissolve minerals, and rise where pressure and permeability allow. As they rise, they can warm shallower sediment and feed surface expressions such as mud pots and steam vents. The magma-related heat remains deep, while the water becomes the messenger that carries its effects upward. The Salton system is especially intense because the crust is young, hot, and heavily sedimented. Thick sediment changes the way heat appears at the surface. In an exposed volcanic field, lava flows and ash might make the magmatic setting obvious. In this basin, the sediment blanket hides much of the igneous structure. It also supplies water, salts, organic material, and minerals that react with heat. The result is not a clean volcanic cone, but a geothermal field rich in hot brine and chemical alteration. The frightening surface name becomes less accurate than the quieter scientific reality. The system is not less powerful because it is buried. It is simply expressed through mud, gas, salt, and heat rather than through flowing lava. The cooling of magma underground is slow because rock is a poor conductor compared with moving water, and because large bodies of hot material lose heat over long periods. Even after magma fully crystallizes into solid rock, the surrounding region can remain warm. Heat stored in the crust can continue to drive geothermal circulation. New intrusions can add more heat if magmatic activity continues over time. Observations suggest that the Salton region has had recent volcanic and intrusive activity in geological terms, but the details of present molten material at depth remain uncertain. Heat measurements show the system is active, while the exact distribution of magma or still hot intrusions is difficult to define. Magma also changes nearby rock chemically. Hot fluids released from or heated by magmatic bodies can alter minerals, create clay, deposit silica, and move metals. In the Salton geothermal field, hot brines can carry large amounts of dissolved solids, including elements that interest scientists and industry. These fluids are not pure magmatic liquids. They are waters that have interacted with sediment, rock, heat, and possibly magmatic gases. Their chemistry reflects mixing and reaction over time. This makes the heat source part of a broader geochemical system, not just a hot object underground. The pressure of magma and heated fluids can also affect cracks in the crust. When hot material intrudes, it pushes rock aside. When water heats, expands, and becomes pressurized, it can enter fractures. When minerals precipitate, they can seal cracks. When pressure rises again, new cracks may open or old ones may reactivate. These processes help create a changing network for fluid flow. The surface mud pot is far above this deeper heat region, but its existence depends on the long chain of energy transfer from hot rock to water, from water to sediment, and from sediment to gas and mud. It is important to keep the scale clear. The mud feature at the surface is small and shallow. The magma-related heat source is deeper and larger. The two are connected by process, not by an open pipe of lava. There's no need for molten rock to be rising directly under a mud bubble at any given moment. Heat can travel through rock and fluid, and the surface may respond far from the deepest heat body. This is why the feature can look volcanic while not being a lava volcano. It is a geothermal expression of a magmatically warmed plate boundary. In this region, the hidden source of warmth becomes the main focus. Observations indicate that the Salton Sea geothermal field is powered by high heat flow associated with crustal extension, young igneous activity, and hot intrusions beneath a sediment-filled basin. It remains uncertain how much molten material exists at depth now, how it is shaped, and how quickly it is cooling. What is known is enough to explain the surface activity without turning it into a simple eruption story. The inner heat source is quiet, buried, and persistent. It warms rock, drives brine circulation, alters minerals, and allows a low patch of mud on the desert floor to behave like a small window into a much hotter crust. Within the same deep geothermal and tectonic setting, the next region is the earthquake link, where heat, fluids, faults, and stress meet in the shallow and middle crust. An earthquake is a sudden slip on a fault that releases stored energy as waves through the ground. In the Salton region, earthquakes belong to the active plate boundary, but they also occur in a crust that is hot, fractured, and filled with moving fluids. This combination does not make every small tremor unusual. It means that the causes and patterns of shaking must be understood through several connected processes. The ground is pulled, broken, warmed, wetted, and sometimes disturbed by human use of geothermal resources. Small earthquakes are common around the Imperial Valley and the southern Salton Sea. Many are too weak for people to notice, but instruments record their locations and depths. These small events often form clusters or swarms. A swarm is a group of earthquakes occurring close together in time and space without one clearly dominant main shock. Swarms can happen in geothermal and volcanic areas because fluids, heat, and fault stress can change together. They can also happen along ordinary tectonic faults where stress is redistributed. A swarm does not automatically mean a large earthquake will follow. It is a signal of active crustal adjustment, and it must be interpreted with caution. The main source of regional earthquake hazard remains plate motion. The Pacific Plate and North American Plate continue to move past one another, and the faults between them store strain where they are locked or partly locked. The Southern San Andreas Fault is one of the major structures of concern in this broader region. It has not produced a very large rupture along its southern section in historical time, and geological evidence shows that large earthquakes have occurred there in the past. The Salton region sits near this important end of the fault system, where the plate boundary becomes more complex. This setting makes earthquake science especially important. Fluids influence faults by changing pressure within cracks and pores. When pore pressure rises, it can reduce the effective normal stress that holds fault surfaces together. In simpler terms, pressurized fluid can make it easier for a fault patch to slip if the fault is already stressed. This principle is well established in earthquake physics. It does not mean fluid alone creates tectonic stress from nothing. It means fluid can help decide when and where stressed rock releases energy. In geothermal fields, natural fluid circulation can contribute to small earthquakes, and changes caused by pumping or injection can also influence seismicity. Geothermal energy operations must manage this relationship carefully. Hot fluid may be brought to the surface through production wells, and cooled fluid may be returned underground through injection wells. Removing and injecting fluid can alter pressure and temperature in the reservoir. Cooling can make rock contract slightly. Pressure changes can move through permeable pathways. These effects may trigger small earthquakes under some conditions. Operators and scientists monitor seismicity to understand how the reservoir responds. This monitoring is part of responsible geothermal development, because the same hot fluid system that provides energy also interacts with faults. Natural geothermal systems can produce similar kinds of small adjustments without human activity. Hot water rises, cools, deposits minerals, seals pathways, opens others, and changes pore pressure. Gas separates, sediment compacts. Fault zones shift slowly or suddenly. These natural changes may be enough to produce small earthquakes in an already stressed crust. The difficulty is that natural and human influence processes can overlap in the same region. Careful records of time, location, depth, magnitude, well, operations, and fluid pressure are needed before causes can be assigned. Scientific caution is important because the crust rarely gives one simple answer. Heat changes the earthquake link in several ways. Hot rock can be weaker than cold rock. It may deform slowly instead of breaking sharply at certain depths. Minerals in fault zones may alter to clays that slide differently from stronger rock. Fluids heated by geothermal energy can carry dissolved minerals that later precipitate and seal cracks, changing where pressure builds. Temperature also affects how deep brittle earthquakes occur. Brittle means the rock breaks suddenly rather than flowing. In hot regions, the lower limit of brittle behavior may be shallower than in cooler crust. This can shape the depth pattern of earthquakes. Earthquake waves travel through the basin in ways influenced by sediment. Thick, soft sediment can amplify shaking at the surface compared with harder rock. Amplify means increase the strength or duration of motion. Basin geometry can also trap and reflect waves. The Salton Trough contains thick sedimentary fill, and this matters for how shaking may be felt in lowland areas. A fault rupture begins in rock, but the experience at the surface depends on the materials above it. Soft sediment, shallow groundwater, and loose deposits can increase certain hazards, including stronger shaking, settling, or liquefaction in susceptible areas. Liquefaction is when saturated sediment temporarily loses strength during shaking and behaves more like a fluid. Mud pots and gas vents are not themselves the main earthquake danger. They are small surface expressions of a broader system. Their presence shows heat, gas, water, and weak sediment near the surface, but major earthquake hazard comes from the large faults and regional plate motion. Still, the same conditions that feed mud features help reveal the active nature of the crust. A bubbling vent and a small earthquake swarm may both belong to a setting where fluids move through faults. They should not be treated as the same event. but they are related through the environment that allows them. Scientists watch the region with seismometers, ground deformation measurements, global positioning instruments, satellite radar, gas studies, and well data. Seismometers record shaking. Global positioning instruments measure slow ground motion. Satellite radar can detect subtle changes in ground height across broad areas. These tools help show whether the crust is moving steadily, swelling, sinking, or breaking in small events. The data can improve models of how strain is building or releasing. Even with strong monitoring, earthquake prediction in the sense of naming an exact time, place, and size remains beyond current science. Hazard assessment instead works with probabilities, past records, fault behavior, and physical understanding. The earthquake link also includes uncertainty. A swarm may fade without larger rupture. A major fault may remain quiet while strain continues to build. Small earthquakes may occur after fluid pressure changes, but the connection may be clear in one case and unclear in another. A mud vent may change after shaking, or it may continue as before. Observations indicate that heat, fluids, and faults interact strongly in the Salton region, and that both natural geothermal circulation and human geothermal activity can influence small seismic events. It remains uncertain how any specific small event changes the probability of larger fault rupture unless studied in its full tectonic context. In this region, the hidden system becomes less like a single vent and more like a living stress field, though the process is not alive. The crust stores motion from the plate boundary. Fluids move through fractures. Heat alters strength. Sediment changes, shaking near the surface. Small earthquakes mark moments when a fault patch slips, sometimes quietly below the threshold of human notice. The burning volcano at the surface is not the earthquake source, but it stands within the same restless framework. Its mud, gas, and heat are shallow signs of a deeper crust where pressure, motion, and release continue in slow and sudden forms. Beneath the earthquake link, the next region is the deeper Salton Trough, the long sediment-filled depression where the crust has been pulled apart and lowered over geological time. A trough is a low structural region, shaped not only by erosion at the surface but by movement of the crust itself. In this setting, the trough forms the northern landward continuation of the Gulf of California rift system. Its surface may appear as desert, farmland, lake margin, and geothermal field, but its deeper body is a thick buried archive of subsidence, sedimentation, heat, faulting, and gradual crustal change. The shallow mud pots sit far above this larger structure, yet they belong to its upper skin. The Salton Trough is filled with many layers of sediment. Much of this material is linked to the Colorado River and to changing lake and basin environments through time. Sand, silt, and clay have been carried into the low region and deposited again and again as rivers shifted. Floods spread, lakes expanded, and dry intervals returned. Over long periods, the weight of these deposits has become immense. New sediment buries older sediment. Water is squeezed from some layers. Grains compact. Chemical reactions slowly alter minerals. What begins as loose material at the surface becomes deeper, warmer, denser, and more strongly pressed with time. The thickness of sediment in the trough is one of its defining features. In places, the fill reaches several kilometers deep. All numbers are approximate because the deepest structure varies across the basin and is known through geophysical studies, drilling, and interpretation rather than direct view everywhere. This thick fill hides the rifted crust beneath it. In an ocean basin, Spreading may create volcanic seafloor that can be more directly connected to deep processes. In the Salton Trough, sediment arrives so quickly and in such volume that it blankets much of the tectonic activity. The result is a rift environment concealed under river-built and lake-built deposits. As the crust stretches, the basin continues to make space. This is the process of accommodation, meaning the creation of room where sediment can accumulate. Subsidence makes the land lower relative to surrounding areas. Sediment fills the space. More movement creates more space. More sediment arrives. This repeating relationship allows a very thick sequence to build. The trough is therefore both a product of tectonics and a recorder of surface environments. The lower layers hold the memory of older rivers, lakes, floods, and shorelines, while the structure holding them open comes from deeper plate motion. The deeper sediment does not remain cold. Heat rises from below, and burial itself also changes temperature. With depth, the sediment enters hotter conditions. Water trapped between grains becomes warmer and more reactive. Organic material may break down. Minerals may dissolve, transform, or grow. Clay minerals can change with temperature and pressure. Salts can move in solution. The deep trough is not simply a pile of dry layers. It is a warm, compressed, fluid-bearing body where chemistry and physics continue quietly after deposition. This makes the sediment fill part of the geothermal system rather than only a cover above it. Compaction is a slow but important process in this region. Loose sediment near the surface contains open spaces filled with water, gas, or air. As more layers are added above, pressure increases. Grains are pushed closer together. Water is forced out where pathways allow it. Clay-rich layers compact differently from sand-rich layers. Some layers may become overpressured if water cannot escape easily. Overpressure means fluid pressure is higher than would be expected from a simple open connection to the surface. Such zones can influence fault behavior, fluid movement, and the stability of sediment. The deep trough is therefore a pressure system as well as a structural basin. The crust beneath the trough is thinner and more altered than stable continental crust. Rifting stretches it, faults divide it, and heat changes it. In places where extension continues long enough, continental crust can give way to new oceanic crust. In the Salton Trough, the process is complicated by the enormous supply of sediment. The boundary between highly stretched continental crust, intruded crust, and new igneous material is not visible at the surface and is not simple everywhere below. Scientific studies indicate that magmatic intrusion and rift-related processes are present, but the deep geometry remains complex. This uncertainty is part of the scientific reality of the region. Faults extend through the trough at different depths and angles. Some cut the sediment fill, some connect deeper crustal blocks, some may end upward within layers that bend rather than break clearly. The thick sediment can hide fault traces and spread deformation across broader zones. At depth, faults may guide hot water, brine, and gas. They may also separate blocks that subside at different rates. A layer deposited as a flat bed may later be tilted, stretched, or offset. The trough's interior is therefore not a neat stack. It is a layered body disturbed by continuing movement. The deep brines of the region are shaped by this setting. Water trapped in sediment and water circulating through faults encounter heat, salts, and minerals. As temperature rises, the water becomes more able to dissolve material. It may become dense and highly saline. These brines can carry metals and other elements in solution. Their chemistry reflects long contact with buried sediment, igneous heat, and fault pathways. At shallower levels, These fluids may mix with cooler groundwater or remain isolated depending on permeability. The deep trough supplies the storage space and reaction environment for much of this fluid history. The Salton Trough also shows how a quiet surface can sit above crust in transition. Stable continental interiors often have thick, cooler crust and low heat flow. Mature ocean basins have different crust and different heat patterns. The Salton region lies between categories. It is continental land, but it is part of an active rift-transform boundary. It holds thick river and lake sediment, but beneath that cover, the crust is being stretched and intruded. It is not a simple desert basin in the ordinary sense. It is a place where a continent is being modified from below, while sediment keeps smoothing the surface above. This region also changes the meaning of time. Surface mud bubbles may shift in minutes, shorelines may move over years and decades, earthquake swarms may last days or weeks. The trough forms over hundreds of thousands to millions of years. Each grain of sediment is small, but the accumulation of grains becomes kilometers of fill. Each year of plate motion is small, but the total movement opens a basin. Each pulse of heat is hidden, but the long heat flow alters deep layers. The inner structure of the trough is a slow record of repeated small changes becoming a large geological body. In this region, the burning volcano is distant in scale but still connected. Its mud is made from sediment that belongs to the basin fill. Its heat rises through the stretched crust below. Its gas and water follow paths shaped by faults and pressure within the trough. Observations indicate that the Salton Trough is an active, sediment-filled rift basin where crustal extension, rapid sedimentation, high heat flow, and fluid circulation occur together. It remains uncertain in detail how deep crustal boundaries are arranged beneath all parts of the basin, because thick sediment hides direct evidence. The trough is the deep container of the system, a lowered and warming body of layered earth, where the surface disturbance becomes only the smallest visible sign. Beneath the deep sedimentary trough, the next region is the mantle influence, where heat from below supports the thinning, warming, and slow transformation of the crust. The mantle is the thick layer of earth below the crust. It is not a global ocean of liquid rock. Most of it is solid, but over long time it can flow because it is hot and under great pressure. In rift and plate boundary regions, mantle heat can rise closer to the surface than it does beneath older, thicker continental interiors. This deeper warmth is one of the reasons the Salton Trough is not only a basin of sediment, but a place where the crust is being changed from below. The upper mantle beneath an active plate boundary is part of a moving Earth system, as plates shift and the crust is stretched. Hot mantle material can move upward to occupy space created by extension. This upward movement is not fast in the human sense. It belongs to geological time, with the motion measured across thousands and millions of years, yet the effect is strong. Rising mantle reduces the distance between deep heat and the surface. It can promote melting in small amounts where pressure decreases. It can help feed intrusions into the crust. It can raise heat flow through the basin. The surface mud feature is far above this region, but its warmth begins within this deeper thermal setting. Melting in the mantle can occur when hot rock rises and pressure drops while temperature remains high. This is called decompression melting. The rock does not need to become entirely liquid. A small fraction can melt between solid mineral grains. That melt can gather, move upward, and enter the crust. In rift systems, this process helps create magma that may intrude into the crust or erupt at the surface. In the Salton region, thick sediment and complex faulting conceal much of this process. The mantle influence is therefore read through heat flow, seismic studies, volcanic rocks, gravity measurements, and the chemistry of igneous material rather than seen directly. The mantle also helps explain why the region is part of a wider pattern extending toward the Gulf of California, south of the Salton Trough. Spreading has opened parts of a young ocean basin. There, mantle upwelling and magmatism are part of the creation of new crust. Northward, the process becomes buried beneath sediment and modified by transform motion. The Salton region stands near this transition, where continental land is affected by forces more often associated with ocean opening. The mantle beneath it does not announce itself at the surface with a single dramatic sign. It contributes steady heat and supports the tectonic conditions that make the basin active. Heat from the mantle enters the crust in layers of effect. First, it raises the temperature of the lower crust. Then it helps generate or sustain magma intrusions. Those intrusions warm surrounding rock. Hot rock warms deep water and brine. Moving fluids carry heat upward into shallower sediment. At the surface, mud, gas, and mineral crusts respond. The chain is long and indirect, but it is continuous in physical terms. Energy moves from deeper earth to higher levels through conduction, intrusion, and fluid circulation. The visible surface activity is only the last small expression of a much larger heat transfer system. Seismic waves help scientists infer mantle structure. Earthquakes send waves through the earth, and those waves change speed depending on temperature, composition, melt, and rock properties. Slower seismic velocities can suggest hotter or partly molten regions, though interpretation requires care. Gravity measurements also help, because rocks of different density affect the gravitational field slightly. Heat flow measurements show how much thermal energy reaches shallow levels. Together, these tools allow scientists to describe the mantle influence without direct access. No drill reaches this region beneath the Salton Trough. The mantle remains known through signals that pass upward. The mantle's role does not mean the surface is about to open into a fiery eruption. Mantle heat is a background condition that shapes the crust over long periods. Magma may form and intrude, but it can stall and cool underground. Heat may remain trapped in rock and water rather than breaking through as lava. The Salton geothermal system shows that deep heat can be powerful without producing a classic volcanic landscape. This distinction is important. The mantle influence is real, but it works through depth, pressure, time, and pathway. Its surface signs are filtered through kilometers of crust and sediment. The upper mantle also affects the strength of the crust above it. Hotter, lower crust can be weaker and more able to stretch. Cooler upper crust may break on faults. This contrast helps create a system where deeper levels deform slowly, while shallower levels fracture and slip. As the mantle supplies heat, it changes how the overlying crust responds to plate motion. The basin can continue to subside, faults can remain active, and geothermal fluids can circulate. The region's surface calm rests above a vertical structure in which strength, temperature, and motion change with depth. Composition matters as well as heat. Mantle rock is rich in minerals such as olivine and pyroxene. When small amounts of melt form, the melt has a different composition from the remaining solid. As it rises and interacts with crustal rocks and sediments, its chemistry can evolve. The rhyolite domes near the Salton Sea reflect silica-rich magma, which likely involves processes within the crust as well as deeper melt supply. This shows that mantle influence is not a simple upward delivery of one material. It begins a chain of melting, movement, storage, cooling, and chemical change. Fluids can also be linked indirectly to mantle and magmatic processes. Magma can carry dissolved gases, including water vapor, carbon dioxide, and sulfur compounds. Some gases may separate from cooling magma and enter hydrothermal systems. Hydrothermal means involving hot water. These gases can mix with fluids that also have sedimentary and biological sources. By the time gas reaches a mud pot, it may carry a mixed history. It may not be possible to assign every molecule to one origin without careful isotopic and chemical analysis. The mantle influence lies at the deepest end of that mixture, adding heat and sometimes material to the system above. Time in the mantle region is very slow. The heat that shapes the Salton Trough is not a brief event. It belongs to the continuing evolution of a plate boundary. Over millions of years, extension, transform motion, magmatism, sedimentation, and subsidence work together. The basin may deepen, fill, heat, and change as the boundary evolves. Surface features may appear, disappear, or migrate as shallow conditions change. But the deeper mantle influence persists as part of the regional tectonic system. The contrast between slow deep motion and active shallow bubbling is one of the central scientific facts of the place. In this region, the explanation reaches below sediment, faults, fluids, and crust into the source of sustained warmth. Observations indicate that mantle heat and upwelling related to plate boundary extension help support high heat flow, magmatism, crustal thinning, and geothermal activity in the Salton Trough. It remains uncertain in fine detail how melt is distributed beneath the region at any present moment, because the deepest evidence is indirect. The mantle influence is not visible as flame. It is the deeper thermal condition that makes the upper system possible. It warms the crust from below, helps feed hidden intrusions, and gives the quiet basin its long, deep source of heat. At the innermost meaning of the system, the burning volcano becomes a surface sign rather than a single object. It is not one simple threat rising from one simple source. It is the meeting point of desert climate, lake margin sediment, geothermal water, escaping gas, mineral crust, faults, plate motion, magma-related heat, and mantle warmth. Each layer adds something, and none of the layers explains the whole feature alone. The surface mud needs soft sediment, the bubbles need gas. The heat needs a geothermal source, the pathways need fractures, the basin needs tectonic motion, the deeper warmth needs the larger plate boundary and mantle setting. The feature is small, but the system behind it is wide and deep. Its terrifying quality, when described carefully, is not the image of a fiery mountain. It is the quiet fact that ordinary ground can belong to a complex active earth system. A pale crust can hide wet mud. A still surface can cover gas. A low basin can sit above hot brine. A desert flat can be part of a plate boundary. The danger is not made larger by exaggeration. It is already serious in plain terms. Hot mud can injure. Weak ground can collapse. Certain gases can become harmful in poorly ventilated places. Faults can produce earthquakes. Dust from exposed lake bed can affect air. These risks are different in scale, but they share the same setting. The burning appearance is therefore a translation of deeper processes into visible form. Heat darkens and softens mud. Gas opens bubbles. Minerals stain the surface. Steam appears when warm vapor meets cooler air. Salt crusts break and reform. The ground looks alive, but it is not alive. It is responding to pressure, temperature, chemistry, and gravity. The movements are small expressions of physical law. They repeat because the conditions below continue to supply energy and material. In this sense, the surface feature is a natural instrument, registering changes in the shallow ground. The name volcano remains useful only if it is handled with care. It points toward upward movement from below, but it can mislead if it suggests lava, ash, and a steep cone. The California feature is better understood as a geothermal mud system in an active rift and transform boundary. Its mud eruptions are not magmatic eruptions. Its gases are not proof of an open lava conduit. Its heat does not require molten rock at the surface. The word volcano belongs to resemblance more than mechanism. Scientific description replaces the dramatic name with a layered explanation. The system also shows how uncertainty works in Earth science. Observations can confirm high heat flow, active faults, hot brines, shallow gas release, unstable mud, and recent igneous history in the region. Measurements can identify temperatures, gas chemistry, mineral composition, and ground movement at specific places and times. Yet the exact underground paths remain partly hidden. A vent may change because a shallow passage clogs. A nearby opening may become active because pressure shifts. A small earthquake swarm may occur for reasons that require careful study. The unknowns do not erase the known facts. They define the boundary between evidence and speculation. The most important understanding is connection. The Salton Sea margin is not separate from the geothermal field. The geothermal field is not separate from the fractured crust. The fractured crust is not separate from the plate boundary. The plate boundary is not separate from deep heat. At each inward level, the system becomes less visible and more fundamental. The outer landscape gives shape. The inner processes give energy. The surface mud pot is where these levels meet in one small place. It is a point where the deep earth becomes touchable, though not safe to touch. Human presence adds another layer of meaning. Roads, farms, canals, power plants, and communities exist near this active ground. Geothermal energy offers a useful source of electricity because the Earth's heat is unusually accessible here. At the same time, the same heat and fluids require careful monitoring. Water management affects the Salton Sea margin. Exposed lake bed affects dust. Infrastructure crosses a region of soft sediment and faults. Scientific knowledge matters because it helps separate imagined danger from real hazard. A calm explanation does not make the place harmless. It makes the hazard clearer. The feature also belongs to time. In a moment, a bubble opens and collapses. In a day, steam changes with air temperature. In a season, mud dries or wets. In years, shorelines shift and vents may migrate. In centuries, earthquakes mark fault movement. In millions of years, the trough opens, fills, warms, and changes as plates continue to move. The small surface disturbance is brief, but it is tied to processes that outlast any single observation. This contrast gives the place its scientific weight. It is a small sign of a long transformation. At the deepest level of meaning, the burning volcano is not hiding one monster beneath the mud. It is hiding complexity. It is hiding the fact that the ground is part of a boundary where a continent is being altered. It is hiding hot water under pressure, gases moving through pores, minerals forming from vanished water, faults storing strain, and heat rising from far below. These are not myths of disaster. They are ordinary Earth processes concentrated in one unusual place. The surface looks strange because many processes overlap there. The final explanation remains steady. The California burning volcano is a mud and gas feature in a geothermal landscape near the Salton Sea. It is powered by heat from an active tectonic setting, shaped by water and sediment, and expressed through bubbling, crusting, steaming, and ground weakness. Observations indicate that it belongs to a broader system of high heat flow, buried faults, hot brines, and plate boundary motion. It remains uncertain in fine detail how each shallow vent connects to each deeper pathway at any moment. What is known is enough to make the feature meaningful. It is not a simple volcano. It is a quiet opening in a layered earth, where the desert floor shows the presence of heat, pressure, chemistry, and movement below. At the surface, the basin remains broad and pale beneath the sky. Heat still moves through hidden rock. Water still follows small openings below the ground. Gas still gathers, rises, and escapes where the sediment is weak. Salt and minerals still mark the places where water has vanished into dry air. Nothing in this setting needs to hurry in order to be powerful. The earth works slowly here, through warmth, pressure, motion, and time. The mud pot settles into its place as one small sign within a much larger structure. It is not a mountain of flame. It is not a simple opening to molten rock. It is wet sediment stirred by gas and heat, resting above a basin shaped by faults and deep thermal flow. Its surface may bubble for a moment, then smooth again. A rim may dry, a crust may break, a faint plume may rise and fade into the desert air. Each movement is part of the same calm explanation. Around it, the Salton landscape remains layered: shoreline, salt flat, geothermal field, fractured crust, plate boundary, and mantle heat all hold their positions in the story. The outer land appears open and still, while the inner earth continues its quiet work. Scientific understanding does not remove the mystery. It gives the mystery a shape that can be studied, measured, and respected. The burning volcano hides no single dramatic secret. It hides a system. It hides water under pressure, gases in motion, minerals forming, faults shifting, and heat rising through a changing basin. In the slow desert light, the surface becomes calm again, and the deep earth remains beneath it, warm, patient, and unseen.